Started. So thank you for joining everyone, and good evening, morning, or afternoon to everyone, depending on your time zone. Before we begin, I just want to let everyone know that the closed captioning feature is on, so please feel free to use that if you would wish, if you would like. And then the Q&A and chat features are both enabled, and if you have any questions, feel free to put them in there, but we will get to them at the end of the webinar. And the last thing before we get started, I want to just throw out that we are looking for more speakers for 2026. And so if you have any speakers or topics you would like to suggest, I will put the link to that form in the chat. So without further ado, I want to welcome today's speaker, Dr. Ake Fagereng, who is a professor in structural geology at Cardiff University and received his PhD from the University of Otago in 2010. His research interests lie in how the Earth deforms and how this deformation is recorded in rocks. Today, he will be discussing the range of fault slip styles on subduction zone interfaces and the controls of this continuum of behaviors. Thank you very much for joining us. And without further ado, the floor is yours.
Thank you. Let me just try and share here as well. All right. Thanks very much for the invite to give a webinar. And yeah, like I said, I thought I'd try and spend this time talking about some geological constraints we have on the behavior of the subduction plate interface, given this is a subduction community. I should say, everything I say here is really coming from work of lots of other people, especially Adam Beale, Harry Lee, and Chris Tully, who were postdocs and grad students with me for several years until recently on some ERC-funded work. And then I'm also lifting quite a lot of work from IODP 375 offshore New Zealand. And yeah, so, acknowledging everyone else, and I'll hopefully just remember to refer to them as we go. So, the rationale for looking at geology of subduction interfaces is we know that, as I'm sure this audience especially knows, all the instrumentally recorded magnitude 9s have been on subduction interfaces, so they're capable of very, very large earthquakes. But at the same time, there are many subduction zones that seems not to generate that kind of earthquakes. So there is a hazard perspective of, can we understand what controls that difference between a megathrust that has a magnitude 9 and a megathrust that mostly just creeps silently at plate rate, or generates slow transients like slow slip events. So there's a classic model that does a good job of explaining a lot of that. Just get a pointer. So going back to Hindman 97, we've got this model of that there is a locked zone that is determined mainly by temperature, that there's an up-dip limit of about 150 degrees, above which earthquakes tend not to nucleate, and a down-dip limit of about 350 degrees, below which earthquakes tend not to nucleate. And then the size of that locked zone is one of the main controls on how big an earthquake you can get. There's also an interplay here with that. If the moho is very shallow or shallower than the 350 degree limit, then the moho would instead be the control on the down dip limit. So that's a nice basic rule of thumb model. It fits broadly also what we see from geology, going back to Simpson's 1977 links between fault rocks and fault mechanisms, that at shallow levels we see gouges and discrete faults that would form in frictional sliding, potential earthquake slip, and at some depth that transitions to shear zones dominated by myelonites that probably deform slowly by viscous creep mechanisms. And if we think of the change between those mechanisms, there's a frictional viscous transition where frictional sliding becomes difficult because pressure is high. Viscous creep becomes easier because temperature is temperature is high. And that happens to be at about 350 degrees for quartz, but warmer for say, mafic materials. But that's one of the potential reasons for this magic 350-degree temperature, is that relates to this transition. Or a transition in frictional stability, which is kind of a different way of looking at the same thing. But again, that there are a temperature and depth range where rocks tend to slip fast, or friction tends to be unstable, and you have earthquake slip, and shallower and deeper than that zone, slip is stable, either because viscous mechanisms dominate at depth, or because of dilation or complications with making a incohesive gouge slip fast at low pressures. So this again, there's a model here that sort of works. And if we go and look at, say, the current subduction zone in Japan, we have the Nankai Trough here. And then at shallow levels, there are slow slip events and tremor. Then there's a seismogenic zone where earthquakes occur, segmented for various reasons, but there is a depth range that sort of fits that temperature range talked about earlier. And then below that, there is steady creep. And then in between, there are transitional features now well established, and described as slow slip, so geodetically determined transient creep that doesn't get to seismic slip rates, and tremor events that are low frequency earthquakes that tend to cluster in time somewhat periodically, and down dip of the seismogenic zone, but up dip of the steady creeping zone. So there's a bit more complexity here than in the classic model, in that the transition zone is more complicated. But again, there is this locked zone that has great earthquakes, and up dip of that, some transitional behavior, down dip of that, some transitional behavior, and then stable shear. And Sefer and Tobin added the observation here that these transition zones are also associated with high or extreme fluid overpressures, while fluid pressure is more moderate in the seismogenic zone, and potentially also further down dip. So again, there's some sort of depth division between a transition zone, a seismogenic zone, a transition zone, and steady creep. But another observation you can take from this map is that the seismogenic zone varies quite dramatically in thickness along strike, and there are places where it basically doesn't exist, and there's places where it's wider. Especially clear in New Zealand, where we have a zone underneath Wellington where the locked zone in red, so this is geodetic locking, red is locked, blue is creeping. Taking that as a proxy for the seismogenic zone, then the seismogenic zone or the locked zone is very wide in the south, and then essentially only a few kilometers wide, or tens of kilometers wide in the north. So this northern part of the margin is essentially creeping, and the southern part is basically locked throughout the seismogenic zone, down to a temperature of roughly 350 degrees in most thermal models of this area. While here, the locked zone is, the base of the locked zone is at more like 150 degrees. So this doesn't quite fit the classic model, and this is true for many places. But then if we add slow slip events on here, they basically, again, they're in the transition zone between locked and creeping, but that puts them in the thermally determined seismogenic zone in the north, and down dip of that in the south. So this area has seen a lot of study in recent years. I'm not going to go through anywhere near all of it, but I thought I'd talk a bit about the geological observations we have for this creeping part of the Hikurangi subduction zone. So we go to Gisborne, which is up here in this slow slip patch. This is in more detail, an area of slow slip in red. we have a drill site into a fault zone here near the trench. There's a cross section here along this red line, so we'll go to that. And basically what we see here is a very rough incoming plate because of the Hikurangi plateau and several seamounts. That is, and it's relatively sediment poor. It's a steep accretionary prism. We have a lot of faulting as well in the incoming plate due to plate bending. And we have a few boreholes that were drilled in Expedition 375. One is on this frontal thrust, so you can see the plate boundary in black, and near the trench that steps up onto several frontal thrusts. The one that was intersected at site 1518 was chosen because it has a clear seafloor offset. There's a clear seafloor scarp, so we've take that as a sign that this is a relatively active frontal thrust. It has about 6 kilometers of displacement on it. And then there's also two drill holes in the incoming sequence, which gives us some insights into the materials that might be at the interface further down depth. There's also a borehole out here, which I won't talk about, but that was mostly for instrumentation and long-term observatory. So thinking about what happens at very shallow depth. So we're now at less than 1 kilometer in a active frontal thrust in an area that experiences slow slip. And what we see is a couple of very distinct fault rock types in the core. There are, with some false color overlay here, there's a breccia that's basically blocks of sediment surrounded by other sediment, but clearly broken apart into bits and filled in with finer grain material in between. Associated with that are also layers that look more like this, which is, for anything, look like a ductile fault rock. They are folded, they have these sort of flow bands with asymmetric inclusions that indicate a shear sense. And then there's mixtures of these two sort of styles with flow bands, where I'm using flow bands as a sort of very generic term for something that has been sheared or dragged along. Doesn't quite look like an intact sediment, but at the same time isn't broken in discrete features. Although here there are discrete, mostly normal faults, offsetting these flow bands. So there is mixture of very brittle descriptively ductile layers, and a mixture of those two forms of deformation. And if we look at that on a core scale, porosity is relatively constant throughout the fault zone. It gets a little bit higher just underneath it, but otherwise not much sort of depth-dependent variation, which comes from that within the fault zone you have, on the top of it, there's about 18 meters of a mixture of these sort of brecciated layers and the more ductily sheared layers. Then a wider zone that's about 30 meters thick of dominantly ductile deformation, and then another zone of mixed brittle ductile for about 10 meters underneath that. So we're at 300-meter depth, and we have a fault zone that is about 60 meters thick, which is not that unusual. If you look at similar fault zones drilled in Nankai, Costa Rica, Barbados, so forth, they are tens of meters thick, and they tend to have this mixture of brittle and ductile deformation features already at this sort of depth. So the interpretation we made from this was that, okay, already at this kind of depth, you have a change in deformation style, whether that's differences in velocity, differences in fluid pressure, whatever it is, it's creating very different fault rocks intermingled at 300 meters depth. So already at that sort of depth, we have a mixture of deformation styles and slip styles along this fault. That's for very, very shallow slip. I should also say there are some indicators of that there has been fast slip on that fault zone based on organic materials from Heather Savage's group. So there does seem to have been earthquake slip on there. We kind of know there's also some slow sliding. So sort of see that mixture of brittle ductile deformation as mixtures of slip speeds over time. If we then go to, but that's very shallow. So if you want to look at what's going on more deeply or further down depth, we look at the input sequence, because here we can drill into materials that you then, if you track them down depth, they become the materials on the interface, as opposed to these frontal thrusts within the accretionary prism that goes through the turbidites that were at the site I just showed from 1518. The materials deeper on the interface come from deeper in the sequence. Deeper in the sequence means this part of the borehole, so 600 meters or deeper at the input site. And here we're not looking at siliciclastics anymore. We're looking at carbonates or volcaniclastics. And the carbonates are dominated by calcite and clays, dominantly calcite, whereas the volcaniclastics are very, very messy. They have P-wave velocities varying from 1.5 to 5.5. And they have clay contents typically that are typically quite high, although in some places you have an altered basalt with hardly any clay. Other places you have basalt that's basically turned into smectite. So you have this very, very heterogeneous sequence of volcanic sediments. That's on the flank of a seamount. We also drilled a seamount, and it's basically the same sort of thing. Thin layer of mud on top, but then the rest of the sequence drilled there is again this very variable volcanic material with very different properties. So, the interpretation of this incoming sequence is that we have incoming seamounts. Some of them are buried, some of them stick out. They have a finite thickness of altered sediments and altered basalt on top or surrounding them. We don't quite know what the interior is like, whether that's in more unaltered or still altered. Although there is some geophysical insights to that's come out later, that there's quite a few varieties of these seamounts. But generally they are, they're not solid blocks of basalt. They're much more complicated mixtures of basalt and altered basalt and sediments, which is also capable of taking quite a lot of fluids with it down depth. And then on top of that, there are carbonates that will also behave differently from how the siliciclastics behave. So if you think of what happens when you subduct that, is we're scraping off the turbidites, and that governs what happens with the splay faults and internally in the accretionary prism. And then this interface itself is governed by how these volcaniclastic materials and carbonates behave as they are undergoing higher pressures, higher temperatures, as they dehydrate and so on, which will be very different from the sort of generic models based on quartz rheology that we showed at the start. So one of the arguments that came out of Phil Barnes's paper on this was that it is a very heterogeneous sequence, and that might be one of the reasons we have a very heterogeneous behavior at this particular margin, and particularly for the generation of slow slip events in this location, because we're dealing with these very fluid, rich, very clay-rich sediments that are related to the seamount. That's what we see in the input borehole. So just want to add this one slide from Harry Lee's PhD, where he looked at receiver functions from an array that was the NZ3D, the NZ3D array that covered a 10 by 20 kilometer rectangle above or just inland of or just on land of the slow slip patch, again in Gisborne. And what he got out of this was that we have very high density of broadband instruments, and he could detect the plate interface as a positive conversion or a positive or an increase in velocities. And one point we could get from this quite high resolution data set was that you can't fit a planar surface to that. It comes out as a very irregular surface, even with this. So the top is drawn there, the bottom is drawn there. Don't take that as an absolute thickness. Think more of that as an uncertainty in its location. But even with that uncertainty, the interface doesn't fit a planar surface. If we take a best fit surface to that and work out the shear stress on it as basically a function of an assumed stress field for the region and the orientation of the interface, then it's relatively flat and relatively low stress at this up dip part. And then as we go down dip, because of a quite sharp bend, the stress on the interface, again, ignoring any changes in fluid pressure, increases quite dramatically as a function of interface roughness. And it goes from quite low to a fair bit higher, and that correlates roughly with where the down dip end of slow slip is. So part of what allows the slow slip might be relatively low shear stresses in this part of the interface relative to just down dip. This bottom diagram is a bit busy, but basically Harry's inferred interface is down here. It fits onto inferences from shallower depth quite well, and it makes the point that the roughness of the interface, at least at 60 to 100 kilometers from the trench, that still remains. It's not like it goes from being rough offshore to being smoother down depth. It's still a irregular rough interface at these depths. All the colors here are geophysical indications of high fluid pressure. So there's an indication of a fluid-rich downgoing plate, which is also shown by decreasing seismic velocities in Harry's model here, which is inconsistent with what we saw in the incoming sequence, in that we think that's basically a few kilometers worth of high or fluid saturated volcanic clastics and basalts in the downgoing plate. So the point of this is what we see offshore in the input sequence is a very heterogeneous sequence. That is still the case if we look at some seismic indicators for what's going on at depth. We can't drill that deep. So since we can't drill the seismogenic zone, we try and go and look at some exhumed faults that might be representative of what's down there. Again, this is from Harry Lee's PhD work. And we went to Anglesey in North Wales. It's close to home for us, but it's also it's a classic location for melanges, mapped back in the early 1900s by Greenlee, and one of the type localities for melanges in the UK. It also is a very similar sequence to what we see in Hikurangi. So as opposed to places like the Shimanto complex or the Franciscan, where there's a lot of turbidites, this place has some turbiditic sediments, but very little. It's dominated by basalts and carbonates. So like the Hikurangi sequence. It's a more complicated map on the left, simplified map on the right. Things are more or less vertical because of later rotation, but we have basalt in green, carbonates in blue, and mudstones and sandstones, or heterogeneous things, in red and orange and brown. And you see basically repeated sequences. So a basalt, then cut off by a fault, then a carbonate sequence with basalts cut off by a fault, and then repeated again. So, the main thrusts here are between basalts and ocean floor sediments, and basically just repeating those sequences. So basalt with carbonate, and then heterogeneous mudstone on top, fault, another basalt. And similarly here, basalt and carbonate that are interlayered, and then more heterogeneous sediments, another fault, and then repeating. So sort of a classic repetition of ocean floor sequences, which is the kind of thing you would get if you were sort of repeatedly underplating bits of the downgoing sequence. So we could interpret this as potentially slices of the megathrust as it steps down and then preserves a slice of what used to be a megathrust into the remnant accretionary prism. So if we believe that, then basically what we see here is that the main fault localizes into ilitic and chloritic melanges. So here is one of the main thrusts that separate to the left terrigenous sediments, and then to the right carbonates and basalts that overthrust that. That's the slice on the left. And the formation here is at about 270 degrees based on chloride thermometry. So there's a bit of an uncertainty on that, but roughly they're high 200s, so inside the seismogenic zone, well under the 350 degree temperature limit that we expect for seismicity, but also quite a bit more than the 150. And generally we see that, well, illite dominates the gouges from the terrigenous material. Chlorite dominates the basaltic derived material. So the basalt, what was once basalt or volcanic sediments, has been turned into chlorite. These are just some examples of what you see in the rocks. So very fine grained, foliated, shear zone rocks with little remnant basalt clasts surrounded, and a bit of calcite surrounded by ilitic gouge on the left and surrounded by chloritic gouge on the right. And if we think about this in detail, what we basically have is low shear strain sands and mudstones, high shear strain within ilitic and chloritic melanges, and then again, pretty much preserved pillow basalts away from the gouges that are generally just a few meters thick. And another example of the ilitic and the chloritic melanges. And if we zoom in on them, there are also some deformed and recrystallized calcite veins in here, as well as smeared basalts that are largely replaced by chlorite. So the rheology here is controlled by essentially illite and chlorite, and within these zones also, you can recognize basaltic clasts here in black that are deformed by some slower mechanism, probably pressure solution. So it seems to fit this idea of this frictional viscous flow in a gouge where sliding is happening on phyllosilicates, and then there are clasts of what used to be basalt in the chloritic melange and what used to be quartz in the ilitic melange that deforms more slowly. Reason I pointed out the deformed calcite is we can use the calcite to get some sort of stress gauge, in that there are recrystallized calcite grains that are free of dislocations and have a more or less consistent grain size that replaces the relic clast. And if we look at the grain size, that's around 11 micron plus minus. If we make some assumptions about temperature, we can turn that, or if we make some assumptions about that's representative for the recrystallized grain size, then that would relate to a stress of about, well, roughly 90 megapascal, but or differential stress of about 90 megapascal, or 30 to 255 megapascal if we look at the whole range of grain sizes. So playing some games following what Melody French and Kelly Condi have done in other places, we take this sequence and say, okay, we have a mix of basaltic rock that is basically governed by chlorite deformation. We have some terrigenous sediments that are governed by illite and quartz. Then those behave a bit differently. If you look at the chlorite part by itself and plot the shear strength against fluid pressure as a lambda value, so a fraction of fluid pressure over vertical stress, then whatever the fluid pressure, it's difficult to have pressure solution in the chloritic melange. So basically it's governed by friction. And obviously that gets easier the higher the fluid pressure. Then for an elliptic melange, it's different because fluid pressure solution in the quartz-dominated matrix is relatively easy. And if at low fluid pressure, frictional sliding is difficult. So we have a zone of low fluid pressure, but low shear stress because of pressure solution, although that depends a bit on slip rate. And then at higher fluid pressure, friction becomes easy and takes over. So we have this, if you think of the shear zone as a whole, at low fluid pressure, frictional viscous deformation of elite melange dominates. And then as we increase fluid pressure, frictional sliding takes over. So it goes from basically viscous to frictional with increasing fluid pressure. If we put velocity into the equation, then thinking of the whole shear zone, at low velocities, shear stresses are low because we're dominated by frictional viscous shear of elite melange. The lower plot shows how the deformation is distributed between elliptic and chloritic melange, so basically between heterogeneous and oceanic sediments. And we go from low velocities, the elliptic melange is deforming slowly by pressure solution. And then as velocity increases, the formation moves. When it does depends on the fluid pressure, which is darker curves is higher fluid pressure. But at higher velocities, basically the slip changes from being frictional viscous flow of elliptic melange to frictional sliding in the chloritic basalt-derived parts of the system. If you want a slow slip rate, you basically need to change the deformation to frictional sliding in the chlorite. So the point here is the shear zone deformation in this setting is a combination of pressure solution of quartz and sliding on phyllosilicate, which is a weak mechanism. It's dominant as long as you have a thick zone deforming at relatively low strain rates. We looked at this in sort of a general case and said, well, the red lines here are shear strength of frictional viscous flow in a quartz phyllosilicate shear zone of some thickness. If it's 100 meters thick, then by 15 kilometers at the thermal gradient for the Hikurangi, so that's about 200 degrees or so, if I remember right. We transition from phyllosilicate friction dominating to this frictional viscous flow. If it's a 1 meter thick shear zone, we need to go deeper and warmer before it takes over. But again, there's a way of getting creep at shallow levels if pressure solution and frictional sliding operate in tandem and control deformation. And in that case, there's a at basically if you have low velocities, low fluid pressures, but a fluid presence, pressure solution controls the deformation. But if we decrease the frictional strength by, say, increasing the fluid pressure, or we increase shear stress locally, then that changes. And we have another effect of pressure solution is it creates clay-rich surfaces that you can slip on. And you tend to see quartz-coated shear surfaces along those weak surfaces. So there's this interplay between pressure solution being easy at some conditions and then lower frictional strength or increased shear stress, frictional sliding takes over within the seismogenic zone. Now, going deeper, we'll have a look briefly from now Chris Tully's PhD work, which was a transect of Kyushu in southern Japan, where we have melanges exhumed from 320 degrees down to about 550 degrees. So it gives a picture of what happens in this deeper zone that is nominally aseismic. And if we look at coastal Makimine, what we see there is deformed quartz classed by probably pressure solution. And again, veins following these pressure solution surfaces. And if we look at the rocks in detail under a microscope, they're basically dominated by very closely spaced cleavage surfaces that are created by pressure solution. You can see dissolved edges of quartz and then clay, remnant clay forming this very intense cleavage. And Kotaruji's model for these rocks is that you have sliding along the bulk by pressure solution slowly, and then periodically fluid pressure is elevated, and you activate frictional sliding, but that's limited in length scale because you only have fluid pressure and low stress over a certain dimension. And then that's where you potentially get your slow slip that doesn't accelerate beyond that. So you get a transitional behavior that's governed by this interplay between pressure solution that is relatively slow and then occasional transients that are fluid pressure driven. If we go to inland Makemine at 370, so we've now gone above the 350-degree thermal limit, we stop seeing these clearly preserved veins. Instead, everything is pretty viscous and ductile. This is basaltic rocks in green, or they're mostly chlorite and actinolite, but ex-basaltic rocks, now green schists, in green, and mudstones in black, and everything is basically flowing viscously. There is no evidence really here of any brittle deformation whatsoever. Anything there is, you can kind of make out some white veins here, is overprinted by viscous deformation. And if we look at it in detail, what we see is if you look at the quartz, there's not really any crystal preferred orientation except in some veins. And all the remnant pyroxenes have stress shadows that are filled by actinolite or chlorite. And the whole system basically looks deformed by some sort of diffusion creep. So very viscous, not really anything brittle. But then if we go down to 550 degrees, deformation in Nishisunogi, so higher temperature, we've got an amphibolite, which is basically a remnant basalt with peelite, so remnant or metamorphosed mudstones on top of it, and a chlorite actinolite schist that takes up most of the deformation. That chlorite actinolite schist looks like this, high shear strains, but also lots of veins that are forming along this new foliation, but also itself sheared. So there seems like we're now back into a regime where some brittle deformation is happening, coincident with the dominant viscous flow. For those interested in CPOs, again, feldspar is not showing any signs of crystal preferred orientation. Some other materials are, like actinolite and the micas. But generally, again, if you look at it in detail, what we're seeing is, again, precipitation of new minerals in stress shadows, generation of a foliation that's made of metamorphic minerals, and little sign of crystal plasticity. So again, it seems to be a diffusion controlled system, but here now we're back into having veins filling cracks, and some of these cracks are quite big. So here's a quartz vein that is, there's a coin, so tens of centimeters in thickness, filled with very blocky quartz. So you need to open that quite quickly and then get crystallized quartz within it without closing it. So fluid pressure is again quite high. And we use this to think about, okay, what is the strength of viscously deforming hydrated oceanic crust? Because what we seem to see everywhere is that basaltic crust during subduction is not really behaving like basalt. It's rather a mixture of phyllosilicates and amphiboles. And if you take, if you rather think of an amphibolite, so just metamorphosed basalt, that should have the strength according to this green line. The orange line is a mica schist, so relatively weak. Our measurements of the stresses in these basalts in Kyushu plot where these red crosses are with some uncertainties. But basically, by 500 degrees, we're down to under 20 megapascals. At 370 degrees, we have a similar strength to what you expect for a mica schist. So about below 350 degrees, or depths deeper than 350 degrees, temperatures above 350 degrees, it seems like basalts, if they are altered, hydrated, metamorphosed, have very low shear strengths comparable to viscous shear in mica-dominated rocks, or even weaker. If we put a frictional strength of gabbro or chlorite on here under fluid pressures of lambda 0.8, so not massive, then compared to a gabbro, we have a frictional viscous transition at about 350 degrees. Compared to overpressured chlorite, that transition happens more at 450. But we're kind of replicating this 350 to 450 degree onset of viscous deformation by considering a altered basalt. And on that basis, so saying, okay, you have a seismogenic zone down to about 350 degrees. Although, again, pressure solution can make that deform ductily if you have conditions for that. And then deeper, we're dominated by viscous creep. But if you have fluid pressure, then you can still get some transient brittle failure. So going back to these three locations, briefly thinking in terms of metamorphic conditions, we did say that at 330 degrees, we see fluid-rich deformation or fluid-rich conditions where we have a mixture of pressure solution and frictional sliding driven by high elevated fluid pressures. That is star 1 here on a diagram of pressure against temperature and stable mineral assemblages. If we look on the right, it's color-coded for fluid content, and you see this first star is basically where we go from 15% H2O, crystal bound H2O in a equilibrium assemblage to about 10%. So we have a release of about 5 mol% fluid, and that's related to breakdown of prehnite. So there seems to, at these conditions where we see veins, we see interplay between pressure solution and friction, there's also a burst of fluids released by metamorphic reactions in these rocks. So this is based on bulk rock compositions of basalt from these locations and PT conditions from these locations. Then when we get to 370 degrees in inland Kyushu, we're well inside this equilibrium assemblage that keeps 10% mol% H2O quite happily, nothing being released. So there's no reason to have local elevated fluid pressure unless it comes in from somewhere else. So that sort of consistent with the lack of brittle deformation. And then for a final destination of 550 degree temperature of deformation, we're at the breakdown of chlorite. And again, a decrease in crystal bound fluids, which means those fluids are released, and potentially a local fluid pressure increase. So, for this particular case study, it seems like the brittle viscous mixed deformation is related to local increase in fluid pressure by some metamorphic reaction. But that fits this PT path and these bulk compositions and might not be translatable directly to elsewhere. But we do have this down dip transition where we go from the seismogenic zone into a viscous deforming zone, where the base of the seismogenic zone, fluid pressures are high. Frictional viscous deformation can happen at very low stresses by pressure solution. So that keeps differential stress low, and we're in this very low effective stress, low differential stress regime, where brittle deformation happens when occasionally fluid pressure is high enough to activate foliation parallel slip. Then we have an area of less local fluid pressure. Maybe some is making its way up, but generally we're where viscous deformation is dominating. And then deeper again, we have an increase in fluid pressure that allows a switch to local transient brittle deformation. I'm going to skip this and just give one last little example of how this might work in some numerical models that Adam Beal presented, where we take the natural fault zone and we simplify it, and we say, okay, actually, we're going to have a fault zone that has a mixture of viscous deformation and velocity weakening friction. And how easily it deforms viscously depends on its width, because if it's wide, shear strain rate is slower. So you have a wide zone where some of it is green because it's actively creeping, some of it is red because stress is too high, or strain rate is too high to be accommodated only by creep. Whereas if we make it thinner, then we have larger areas where viscous creep in green cannot quite keep up with the applied strain rate. So here you have potential for larger earthquakes. On the left, viscous creep is dominating. You can think of that in more in a shear stress velocity regime, where if you have a thin shear zone, shear stress increases with velocity. We get to some maximum that the viscous creep can take, and then we change to frictional dominated system. If we have a wider shear zone, more viscous creep can be activated, or viscous creep is easier to activate, and we can accommodate a higher velocity with viscous creep before frictional sliding takes over. And the point of that is, if we look at that in an earthquake cycle model, and we plot viscosity against distance along fault. So basically what Adam did was have a random viscosity along the fault at some stress. So at top diagram, stress is low. And most places, the deformation is happening viscously. There's only a few asperities where viscosity is too high for deformation to happen viscously. Along those, you get small earthquakes in green happening episodically. Then if we increase stress, then we have more asperities where the viscosity is now too high, and stress accumulates. And then as we go higher stress again, we're able to generate big earthquakes, because basically the viscous creep can't keep stress low. You have higher stresses in more places, and that can interlink. So it's a somewhat simplified model, but it does seem to generate, just by variations in viscosity, behavior that goes from creeping with microseismicity to a fault that has big earthquakes. And Adam also made the point that this is reflected in B values, where a low B value relates to this high stress scenario over here, and a higher B value relates to the lower stress scenarios. And he ran a larger number of scenarios. But point again is that there is basically the main message. You can have a competition between viscous creep, say by pressure solution, and frictional sliding. And depending on conditions, depending on fluid pressure, depending on host rock, different deformation mechanisms are preferable. So the points I've been trying to make is, firstly, the megathrust is a tabular zone, and it can deform by distributed aseismic shear. For example, at very shallow levels in Hikurangi, at seismogenic conditions in, for example, our example from the Anglesey shear zones, and within basaltic rocks at 300 degrees or so in our Kyushu examples by diffusion creep. So obviously very shallow levels, we're dealing with granular flows, but as we go deeper, pressure solution becomes active. But within that megathrust, within that tabular zone, even if it can deform by distributed aseismic shear, if you have a perturbation, say decreased frictional strength by elevated fluid pressure or increased local stress, you can change that. And instead of these sort of ductile deformations or distributed deformation, we get brittle deformation at shallow depth, we get slip along the pressure solution cleavages, or we get slip that cross cuts these diffusion creep shear zones, even at depths of temperatures of 500 degrees plus, if you have some way of going away from that aseismic distributed shear. And I will stop with that slide. And thank you very much, and happy to have some discussion.
Thank you very much. That was an excellent talk. The floor is now open for questions, and we already have one from Keelan Wang, who says, "Great synthesis, Ake. The focus seems to be on very warm subduction zones. How is the knowledge extended to colder or very cold subduction zones where 350 degrees is not reached until some distance down dip of the mantle wedge corner?"
Yeah, thanks, Kelvin. Yep, no, that's absolutely true. The examples we happen to have here are very warm. I think they're easier to exhume. So in that way, it's that's been a focus. I think to some extent it is the same kind of idea. We've had a look at some blue schists from much colder subduction zones, and you still see this distributed creep in rocks that look quite a lot like this image in C in top right. You still have amphiboles that dominate the rheology and seem to be, if they're fine enough grain size, they seem to still deform by diffusion creep. So I think that's still possible, but I think we know a lot less about rheology of very cold subduction zones. And they're obviously also harder to deform viscously because the temperatures are lower. But then pressure is also higher, so that makes it harder to get a frictional failure. So it's a good question. I think it's something we need to really look harder at. But my sort of gut feeling is that as long as it's fine grained and wet, then you still have this wide, potentially wide deforming zone of diffusion creep. Maybe you have more dislocation creep in that setting because pressures are going to be higher, temperatures are going to be lower. Maybe it's harder to get these diffusion creep mechanisms.
Thank you so much. We still have time for a couple more questions, but while people are typing those out, I'm just going to put the link for the webinar suggestions that I forgot to put in earlier. So let's give a couple more minutes while people get their questions ready. Okay, if no one has any further questions, I will give everyone back their last 5 minutes of this hour. I want to thank everyone for joining us and for Dr. Fagereng for taking the time to give such an excellent talk. This talk will be uploaded to the SZ4D YouTube channel later today, so you can rewatch it if you want and send it to friends and colleagues. If you have questions that you think of afterwards, feel free to let us know and we will pass them along. So
Or feel
thank you
free
so
to just
much
email me.
and have a great rest of your day.